going to talk about something I've been working on for probably about 3 years off and on now. So this is some software that's variously called S3Netcdf Python or SemSL or SemST. But yeah, so it's all to do with storing climate data on, well, object stores and disk in this case, and trying to do this in a way that you preserve the metadata for all parts of your storage system. So that's where the semantic part comes from. So I'll keep calling it SGNetcdf Python because that's what the repository is called at the moment. So this is a Python, and it also has components that are written in Python library, and it allows you to read and write PDF files from any storage system that has a S3 type API. So S3 just stands for Simple Storage Solution, and it's a HTTP API, and it's used by object stores, obviously, and also some cloud-based storage, particularly Amazon's solutions for that. So S3Netcdf Python, it allows you to store netcdf3 or netcdf4, and each netcdf file can be split into smaller fragments, and these fragments are then distributed across your storage system, such as so you can have chunks in even various different locations for S3, or you can have some fragments on disk and some fragments on S3 at the moment, and eventually we might support some other storage systems, so you could have some fragments on Google Cloud, for example. And so when you read or when you write a part of a file, so you're taking a slice into an array that that's represented in the netcdf file, it'll read or write only that slice. So, and it'll read and write only to the fragments that are represented in that slice, and it allows the parallel read and write of fragments, and it does this just in time. So just only when the user accesses the slice, it doesn't do any read ahead caching or anything like that. So the library, we've implemented it as a subclass of the standard UData net Python package, which is netcdf4 .dataset, and so we try and, well, I've actually managed to replicate the interface to netcdf4 in S3Netcdf. So it's really, we're aiming for just like a one-line change in code for people to be able to use that, and that line change will be in the import statement at the top of their file. And so it consists of 4 main components. So there's the interface, which, as I said, matches the dataset as closely as possible. There's something called the CFA data model, which I'll explain about in a bit, and that stores the subarray definitions, and it includes an array splitter that will split arrays in a default way, although users can also come up with set the shape of each subarray. So this splitter determines the shape that each subarray, each subarray fragment should be, but the user can also specify what shape they want that to be. It also consists of backends, and this is basically the writing or reading part, so to whichever storage system. So at the moment, there's actually 3 in effect backends. There's 2 that write to S3, and there's 1 that writes to the disk. And then there's various internal managers that manage things like the file locations and connections to the external storage systems and user configuration, but that's also external server configuration as well. Just say this software runs completely in user space. All the user needs to do is use pip in a virtual environment or their system Python to install it. It doesn't rely on any other external servers, only the servers where the data is stored. and they just use the standard S3 interface to those servers. You don't have to, no one has to install anything additional on the external servers either. So this is how the files are arranged. So you have what's called the master array file, and this can either be stored on disk locally or remotely, which is S3 at the moment. And this is in a Netcdf format, and it's got some extra information in there, which is this CFA, and we've gone up a point version to CFA 0.5, which I'll explain about in a little bit. And this file, the master array file, it contains all the locations and of the subarray files and how those subarray files fit into the Netcdf, the original Netcdf file. So this into the master array file. So each master array file, it can consist of a number of variables, like a normal Netcdf file. It has the domains, so the dimension variables and the coordinate data for those dimension variables, and then it contains the information about each of the subarray files, and that is where the name and location of the subarray file, the variable in that subarray file, and also the location in the master array for that. So if you have a temperature variable that has 4 subarray files, then each one of those represents a quarter in the in the master array file. So these subarray files, they can either be remote or on disk as well. I should say the master array file is now Netcdf 4 only format because I've switched to using groups for things. But the subarray files can be Netcdf 3, 4, or Netcdf 4 Classic. So it's all built upon these CFA conventions, which stand for the Climate and Forecast Aggregation Rules, and these describe how multiple CF fields can be combined into one larger field. So so the CFA conventions are just a general set of conventions, but then to actually store them in a Netcdf file, we have these CFA Netcdf conventions. And here it says that they're an extension to Netcdf by JSON encoded attributes. And that was true for CFA 0.4, but CFA 0. And we realized the problem with that. But CFA 0.5 uses groups and variables in groups to represent the subarray file information. So I think I said most of this on the previous slide, that there's the master array file, and it doesn't. Important to know, it doesn't contain any field data. So these are small kilobytes to megabytes in size if you have a particularly large one. And then the subarray files actually contain the data, and these are megabytes to gigabytes in size, ideally. I mean, you could have one that's terabytes in size, but you'd be removing the advantage that the S3 Netcdf Python gives you. So this is like the structure we have, and it mirrors the Netcdf of the CFA, and it mirrors the Netcdf structure quite a lot. So you have a data set, and each data set can have a number of groups, and each group in this case contains a dimension, so that's slightly different because you can have and let's say there's one data set, and there's actually no dimensions in the data set in CFA. The default there's a root group, which so if you have an Netcdf file with dimensions in not in a group, then that will be in the root group in the CFA data set. And then the groups also have variables, and each variable has some partition, and that partition is what contains the information for the subarray files. So there will be, as I say here, there will be this represented as a group nowadays. I'll talk about that in a minute. So as I said, I've been working on this for quite a while. And I've been iterating it slightly, but in the past 6 months, I've actually picked it up and started to develop in a lot more. So it's actually been a complete rewrite of all code. I don't think there's any original code from the 2017 version left. And so one of the major tasks was to rewrite the pluggable backends as Python file object. So this is. Someone have a question? Sorry, someone. No, okay. So these are like file objects, similar to when you get a file handle back when you use open in Python. And so they have seek, tell, read, and write, and so on. And so these are controlled on a per server basis, and they have a user config file. There's a S3 backend at the moment, and also an async IO version of the S3 backend. So that's actually made it quite a lot more performant because we're not waiting for there's no blocking IO in that version. So there's also pluggable parsers for the CFA format. So this allows, at the moment we've implemented this for Netcdf 3 and Netcdf 4 parsers, but in future we could allow other file formats such as gRib or PP. And the previous 2017 version was reliant on a disk cache, but we've rewritten this, and the people who implement Python, the Netcdf 4 Python library, kindly added a feature to allow us to recover the memory when you do a write to memory in the underlying Python Netcdf library. And so we've been able to now do it completely cacherless. So there's if you read and write to a POSIX disk, it's performed on disk still because that's the most performant way of doing it. But if you read or write to S3, then it's performed in memory and then streamed directly up to the S3, or streamed directly down from the S3. And here I say there's memory swapping in progress. Because at the moment, if you run out of memory, then it'll raise an exception. But I have a plan to allow memory swapping, which will write some of the data in memory to free up data for more, free up memory to read in more, or write more data. But that's in progress. I've written a structure for it, but I haven't actually filled in the details yet. So yeah, there's a new file format for the master file array file called CFA 0.5, and that's now stored in a group with the same name as the variable, but which has a underscore CFA prefix. And all the variables in the group are the partition information, so that contains the partition matrix shape and the dimensions, and then for each of those, for each subarray file, there's an index location, the variable in the file, the name of the file format, and the shape of the file. And these, this is an example. So these are actually stored in the code. They are represented as a Netcdf group. So if you read from disk, you'll get that benefit that it won't read the entire group in, all the information at once, and it'll only read it in when you do a slice. So this is just a quick example. So it shows you that here the partition matrix shape and dimensions are just single or scalars, and then all the other variables in the partition are multi-dimensional arrays. So you have one of these for each subarray file. So the advantage of this, so the partition information is stored internally as a Netcdf data set with the group variables and dimensions. So what used to happen in the old version of S3Netcdf is that when you opened a master array file, it would read the metadata, which was Netcdf attributes, so a big long string, and then it would actually have to interpret that using like a parser again. And we found that when we tried to do this with very large files or very high resolution climate data that has lots of fragments, then we ran out of memory in the underlying C Netcdf library. So I think it was trying to do it on the stack and it was running out of stack memory. But by doing it in the new way, in the CFA 0.5 way, then it will only read in the partition information when it is needed. When the user takes a slice, it'll only read that partition information when the user takes a slice. And it's both only read and written when the slice is taken. So if you try and read a slice that's not been written, then it will result in missing values being returned for the shape of the array. So yeah, I've written some tools which has made things much easier. So there's now an aggregator, and I'm using this to prepare a CMIP6 example data set, which I had hoped to show today, but time got away from me. And this allows creation of master array files for existing Netcdf files. So if you're aware of CMIP6 data, you have this thing called the DRS, which basically describes a directory hierarchy of where the data is stored. And for, say, the historical run, the data is generally stored in, I can't remember, 20 or 40-year chunks, one of the two. But this aggregator allows you to aggregate for all the variables for a model run, and then all the time periods into one master array file, so the user can address that. They can load that master array file in and then open the take a slice into that and get the data back without having to know what the files are called beyond the master array file. So it's a bit like Xarray's open MF dataset in this case, but you don't even need to know what the name of any of the subarray files are. You just need to know the location and the name of the master array file. So all this kind of gets quite complicated when you've got data distributed, and you can do an NC dump on the master array file, and that will return all the information, but it's a bit difficult to read. So I've written an information tool which allows you to query just certain aspects of the master array file. So you can list all variables or just a single variable, all partitions for one variable or just a single partition, and it shows all the metadata and so on, and dimensions that you'd expect. And I've started writing tests in a more formal way, so there are quite a few unit tests. They're not complete yet and they need some work, but eventually we're aiming for unit tests and then what I call interface consistency tests, so that they run, so that if you run some Netcdf4 Python code using S3Netcdf, then it will work and not throw any errors, and writing tests for that. And eventually aiming for continuous integration on the testing using GitHub's continuous integration. And I'm hoping this will encourage some other people to contribute to it if I make things a bit more formal, because it's only me doing it on about 40% of my time, and that's not even a consistent 40%. So this is the output you get from the information tool. So you see, it looks a lot like NC dump, but you have here like the partition information. So I've requested one group or one variable, the temp variable from the group, and just show me one partition from that. And so here it says the location in the master array is this. It's got this shape. This is where the file is located, and this is obviously a file on my Mac rather than an S3 one, which is the variable and what's the format. and then these are various bits of metadata associated with it. This is UML of the entire system. I won't go through it. The file splitting strategy is quite interesting, but I've covered this quite extensively in other talks. So if time well, I've got till 20 past, I guess. So the files are split by group, then variable, and then each variable is split into subdomains, and these domains form subarray files. And access to the variable data obviously involves reading and writing to the subarray files. And the array splitter optimizes them for 2 reading and writing use cases, and that's either the user reads a single spatial point, a grid box for all the time steps, or the user reads all the data, a field, for a single time step. So these are the 2 use cases. This is you read one grid point to get a time series, or you read the entire field data. And this is the number of operations needed to do each one. And then there's an optimization algorithm that just balances the 2 and decides what size each balances the 2 operations, number of operations for each case, and then decides what size the fragments need to be. So it's just, yeah, it's an optimization algorithm. It's nothing particularly fancy. And now the user can specify which what subarray shape they want as well. And if you use the aggregator tool, then the subarray shape will be whatever is in the file. It doesn't. The aggregator tool doesn't try to do anything smart like splitting the files into smaller fragments or anything. It just takes the files that are already existing and build a master array file from them. So at the moment, there's a nearly feature complete version 2 branch in the GitHub repo. You can use it with 2 caveats. It currently only supports partitions that are uniform in size, so everything has to be, have the same X, Y, Z dimensions in the subarray. And there's no memory management at the moment. If you run out of memory, like reading a lot of subarray fragments into memory, then it will throw an exception at the moment. It catches that it's run out of memory, but it throws an exception. The aggregation tool is fully usable, but it can only aggregate in one dimension, and that might be all that it can ever do, because it's quite difficult to try and aggregate in 2 dimensions without possibly changing the files. And the info tool, that is feature complete and useful. So in the future, and by the future I think I mean the rest of this year, so I need to add the memory management and some non-uniform partition support, and then just document and finish the testing and write a paper and publicize, and hopefully try and get some other people to collaborate and contribute. Yeah, I think we've been doing this for 3 years, and we think it's a really good way of doing it. I mean, it's good that each subarray file is a self-described Netcdf file. So even if you lose the master array file, you can reconstruct it using the subarray files. And we're not aware of any other systems such as ZAR or the system from the HDF group where this is possible. So we think that it's something that's very beneficial if we can get it up to a production quality and get it out the door. So yeah, so I'll stop there and take some questions, please.
Thanks for the talk. Is there any specific question?